Continuing on in section 7.7 here, take note on page 462 deals with exponential decay. Exponential decay can be modeled by the function y equals a times b to the x power. A is still positive, but here our b value is between 0 and 1. The base b is the decay factor, and it's 1 minus the percent rate of change expressed as a decimal. So everything is the exact same between exponential growth and decay, except with decay we're subtracting, we're getting smaller, we're decreasing. So here we take 100% as a decimal, again, that's just 1, and we subtract because we're decreasing our percent rate of change. So whatever that rate is. So here our value is always going to be between 0 and 1, either a decimal less than 1 or a fraction less than 1. But we treat it the same way with everything else as far as calculating things. The only difference is that it'll say something like decrease, so we subtract. In example 3, we're modeling exponential decay. The kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 100 meter increase in altitude, the pressure decreases about 11.5%. What is the approximate pressure at an altitude of 3,000 meters? So here, again, we're going to start off with y equals a times b to the x power. A is still our initial amount. So we're looking for what is the approximate pressure. So our initial pressure at sea level is about 101 kilopascals. B is my decay factor here, and it's a decay factor because we're decreasing. It's going to get smaller. So we're going to take 1 or 100% minus our percent, but again, remember we put that in as a decimal. So to get rid of our percent sign, we move away from our percent sign 2 places, and I get 0.115. So when I subtract here, I get 0.885. And this is my decay factor, what I plug in for B. So 0.885 still raised to the x power. And x is for every 1,000 meter increase in altitude, the pressure decreases. So for every 1,000 meters, that's our x value. So here, my altitude is 3,000 meters. And I'm going to divide by 1,000 to figure out how many changes I've had. Or we can think about it as 3,000 being here. Remember, sea level is at 0 meters. So I'd have 1,000, 2,000, and 3,000. So it's for every 1,000 meter increase. Here I have 1, here I have 1, here I have 1. So 1, 2, 3. And again, we could get that by dividing. So for every 1,000 meter increase, I take 3,000 and divide to figure out how many increases we've had. And we're looking for however many increases we've had as our x. So y equals 101 times 0.885 raised to the third power. And so y, or my pressure, is going to be approximately 70 kilopascals, which I think is kPa. I might be wrong about that. Either way, it's kilopascals. And that's our measure of pressure. So again, the only difference between exponential growth and exponential decay is that exponential decay decreases. So we take our growth, instead of our growth factor where we add to b, here we're going to subtract because we're decreasing, decaying, and getting smaller. Now, using the same situation, so we're going to use the same 11.5% decrease. We're going to start at 101 kilopascals at sea level. But we're going to find the approximate pressure at an altitude of 5,000 meters. So here our pressure is still going to start at 101, that's our initial amount, times, again, our decay factor here, or our b value, is going to be 1 minus, to get rid of our percent, we move 2 places, 0.115 or 0.885. And again, we subtracted here because it's decaying and decreasing. So it's getting smaller. Now we need to figure out how many 1,000-meter increases we've had to get to 5,000. So from 0 to 5,000, we've increased by 1,000 5 times. We can take 5,000 and divide it into 1,000-meter chunks, which is going to give us 5 times that we've reached that change. So here, when I type this in my calculator, I'm going to get approximately 54.8 or 55 kilopascals. Again, it should be smaller because we had more of the decreases. And our decay factor we find by subtracting versus our growth factor that we find by adding. But apart from that, we calculate everything the same way. Real quick recap here. An exponential function can model growth or decay of an initial amount, and that depends on if we're increasing or decreasing. Growth is greater than 1. Decay is when it's decreasing less than 1. And that's all I have for section 7.7.